Welcome to the Explainer. Today we're going to build a complete playbook for any software engineer who's A/B testing LLM prompts. We're talking about going from just a gut feeling that your new prompt is better to actually proving it with cold, hard data.
So let's start with a scenario I'm sure every engineer working with AI has faced. You spent, hours, maybe even days, crafting this brilliant new prompt. It just feels faster, it feels smarter, more accurate. But you know as well as I do, gut feelings and a few cherry-picked examples, they just don't scale. And they're definitely not going to convince your team to ship that thing to production.
Okay, let's dive right in. Here's our roadmap for today. First, we're going to craft prompts that are actually testable. Then, we'll design the A/B test itself, figure out how many users we actually need, and then we'll jump into some Python code. After that, we'll analyze the results and the common traps to avoid, and wrap it all up into a complete AI workflow.
All right, first things first. Look, you just can't run a scientific test on a sloppy or inconsistent prompt. It's impossible. To get reliable data, we have to start treating our prompts less like creative writing and more like a piece of software with a really clear spec.
And this slide just perfectly shows the difference. Look at the left side. That's our baseline, variant A. It's so vague, right? What does helpful even mean? How long is briefly? It's totally subjective. But now look at the right, our challenger, variant B. This isn't a suggestion, it's a spec. It defines the role, the goal, the rules, and a super precise output format. This is something we can actually test.
So what's so cool about this is how it breaks a prompt down into, well, its core engineering parts. When you define the role, the goal, the rules, and especially that output format, you're taking away so much of the randomness. You're reducing variability. And for those trickier, more fuzzy tasks, you can add a couple of solid examples. That's what we call few-shot prompting. It's a great way to guide the model without having to do a whole expensive fine-tuning.
Okay, so we have our two prompts ready for a showdown, variant A and variant B. Now let's get into designing a proper scientific experiment to figure out which one actually performs better.
The absolute key here is randomization. It's the whole magic of A/B testing. By randomly splitting users between the old and new prompt, we make sure our two groups are basically identical. This is so important because it lets us say with confidence that any difference we see is because of our prompt change, and not because, say, all the power users logged on Tuesday morning and happened to get variant B.
And this is the core workflow, the real discipline of it. First, and this is crucial, you have to decide on one primary metric before you even start. Maybe it's the helpful rate. Then you randomize, run the test, making sure nothing else changes, and then you analyze the results. This structure is what stops us from just looking at 20 different metrics and picking the one that makes our new prompt look good.
Okay, now for a step that, honestly, a lot of engineers skip, and it's absolutely critical. We've got to figure out if we even have enough traffic to run a test that means anything. Seriously, running an experiment with too little data is just a recipe for getting a completely misleading result. It's basically a waste of time.
The big concept here is something called statistical power. The best way to think about it is like the sensitivity on your test's radar. The industry standard is 80% power, and what that means is you have an 80% chance of actually detecting a real improvement if it's there. If you run a test that's underpowered, well, it's like trying to find a tiny ship on a huge ocean, but your radar's all fuzzy and full of static. You're probably going to miss it.
So these are basically the four knobs you can turn when you're designing your experiment. For us, the big ones are sample size, pretty simple, more users is more power, and something called the minimum detectable effect, or MDE. The MDE is just the smallest change you actually care about. Think about it. Trying to prove a tiny 1% improvement is real. That's going to take a ton of users. But detecting a huge 20% jump, you can do that with a lot less data.
And the best part is you don't have to break out a statistics textbook and do this math by hand. We can just use Python's stats models library. As you can see right here, you call this one function, plug in your current success rate, that's your baseline, the improvement you're hoping to find, that's the MDE, and your power target, probably 80%, and boom, it'll spit out the exact number of samples you need in each group.
So if we run that code, we get our magic number, 11,500. That means to reliably spot a 15% improvement on a metric that's currently at a 20% baseline, we're going to need about 11,500 users in each group. All of a sudden, this isn't a vague idea anymore. We know exactly what we need to collect before we can even look at the results.
All right, we've got our prompts, we've got our target sample size. Let's get to the really fun part. Let's look at some Python code you could actually drop into your application.
So the first piece of the puzzle is this dead simple randomization function. All it does is flip a coin for every request and assign it to either variant A or B. Now, a quick pro tip. In a real production app, you'd want to make this assignment sticky based on a user ID, so the same person doesn't get a confusingly different experience every time they use your app.
Next up is the main function, the one that kind of runs the whole show. For every request, it figures out which variant the user gets, grabs the right prompt, and makes the call to the LLM. But the most important part is right here, the logging. It's recording everything we need for the analysis later, which variant they saw, how long the response took, and, of course, the outcome that feeds into our main metric.
So, imagine we've run our test. We were patient. We waited until we got all 11,500 samples for both groups. And now it's finally time to dig into the data and see if we actually have a winner.
Okay, so for a metric like latency, which is a continuous number, the right tool for the job is a simple two-sample t-test, and you can get this right out of the SciPy library. It looks intimidating, but this one line of code does all the heavy lifting. It just compares the average latency for Group A and Group B, and it gives us that critical number we've been waiting for, the p-value.
All right, the p-value. It's a notoriously tricky concept, so let's just cut to the chase. Here's what it means in plain English. The p-value is the probability that you'd see this result just by pure, dumb luck, even if your new prompt made zero difference. So a really small p-value, the standard is less than 0.05, means it's super unlikely this was a fluke. It's strong evidence that your new prompt is a genuine winner.
But hold on, before you declare victory and ship it, you have to be aware of these super common traps that can completely sink your results. The biggest one is peeking, checking your dashboard every hour. Just don't do it. It massively increases your risk of a false positive. And also, keep an eye on your guardrail metrics. Sure, your new prompt might be more helpful, but if it's also 50% slower or costs twice as much to run, that's not really a win, is it?
All right, so that brings us full circle. Let's put everything we've talked about together into one single, repeatable playbook that you can use for every single prompt improvement you want to make.
And here it is, the whole shebang, your 6-step playbook. You start by crafting a proper spec-based prompt. You define your metrics and guardrails up front. You do that power analysis so you're not flying blind. Then you implement the code, run the test until you hit your target. And finally, you analyze everything with the right stats and check for those pitfalls. This right here is how you stop guessing and start making real, data-driven decisions about your AI.
So, the big takeaway here is that you now have a complete framework to move beyond just, I think this prompt is better. You've got a rigorous, engineering-led process to improve your AI systems and actually prove the impact. So, the only question left for you is, what's the first hypothesis you're going to go test?